Innovyze educational webinar. My name's Ben Anderson and I'm here as part of the Innovyze team located in our Brisbane office in Australia. So we're going to wait a couple of minutes just for a few extra people joining we can see here. But while we wait, we'll just do a quick introduction of Innovyze for those who don't know who we are. So Innovyze is the global leader for water analytics software. We're very proud to have some of the best tools in the market for sewer, water supply and stormwater flooding. We focus on building rich hydraulic models within modelling tools in these areas and make them accessible for users. We also like to incorporate other holistic functions into the modelling process. So things like asset management with CCTV surveys, condition assessments and renewals plans, along with operational analytics to make those models a little bit more meaningful to everyone who uses them. So what we'll be covering today, we'll be using the specific product InfoWorks ICM. So that applies to stormwater and flooding and sewer networks. We'd like you to be involved in this presentation. So feel free to ask questions. In the GoToWebinar panel, you'll see on the right of your screens, there's a little question box. During the webinar or any time after, feel free to write your questions in there and we'll get to them as we go along or towards the end. If we don't have time to answer your question today, we'll send you a response directly via email as well. So feel free to ask any question anonymously to our team here. And all registrants as well will get access to our CPT certificate. So if you have registered to this webinar prior, we'll email those out in the next day or so. If you're just logged in on one computer with a group of people, we ask that you write down all of the names of the attendees who are there in the room with you and send an email to education@innovyze.com and we'll make sure everyone gets their professional education certificates. So we'll jump right in, introducing our two esteemed presenters today. So we're lucky enough to have Matt, can I call you Matt? Matt Pollard from WSP and the Logan Water Infrastructure Alliance. So Matt's a senior planning engineer who has been the project manager and technical lead for the wastewater planning at Logan Water Infrastructure Alliance for the last 9 years now. So in his role at the Alliance, Matt's been involved in all aspects of planning, including the master planning, detailed planning and feasibility studies, preliminary design, operational analysis for Logan. He's been responsible for the development of the calibration of the council's sewer models, and I hear 80% of council's hydraulic models have now been calibrated. He's a key influencer in the council's shift from a traditional peaking factor approach to wastewater planning, and it's really great to see them move towards calibrated models and overflow containment standards with a much more evidence-based planning philosophy in general. And I've also got Patrick Bonk here from Innovyze. He's our resident sewer hydraulics engineer. Patrick has a master's in engineering design and sustainable infrastructure, and he joined Innovyze in 2014 with a focus and passion towards the emergence of operational analytics, decision support tools, and all of our software enhancements within the context of smart water systems. So thanks for joining us, guys. Take it away, gentlemen.
Thanks, Ben.
Thanks, Ben.
Let's get right to it. So everyone, Patrick Bonk here. I've got Matt Pollard with me. We're incredibly excited to have Matt along for today's presentation and webinar. Matt, how are you doing today?
Good, thanks, Patrick. Thanks for having me.
Feels good to be here.
Yep.
Are you happy about the presentation topic today?
Yeah, it's something I'm pretty passionate about and something I've been heavily involved with the last few years.
For all those attending today, we've written and designed today's presentation to cover three main kind of personas. The first would be if you're in management and your thought process is around how do I get the most out of the models, what we've invested into them, and how do we make better models to be used by more people. The second one would be for somebody who's just getting started out in their modeling journey, whether it's a small council, a larger council, if you're a junior engineer who's just started at council or at a larger utility. It's there's the educational component to develop your skill sets, and lastly, there's A strong technological component when we're thinking time series database within your hydraulic models. How do you connect directly to the data source to improve your modeling practices? So just to overview the topics we're going to be covering today. The first is revisiting modeling objectives. Just asking yourself, why are you modeling in the first place, and revisiting the reasons you're modeling and how you can use it more extensively through your organization. The second main consideration today is, how do we get better organizational integration? How do we get the operations team more involved in the models from a live sewer network perspective? How do we get the field crews getting a better understanding of the network through live operational models? The third main consideration is better calibration. How do we spend less time? How do we have more accurate models? And how do we utilize better tools through our modeling practices? The other one is more effective more effective projects. So how do we get better and do better project work? The other component is better design and engineering works. More up-to-date models. We're going to be introducing a technology called time series database that allows you to connect directly to the data source to have your models more up to date. And with better models, you'll have better levels of service in your network. So continuing on, one of the main inspirations for the topic of increasing your return on your investment of your modeling practices in your organization was a project Matt presented on behalf of WSP and the Logan Water Alliance last year at Innovyze's Brisbane User Day. And it was a great example of great engineering meets great software and excellent project results. And that was captivated in the fact that $250,000 was invested and $18.5 million were saved in capital works. So Matt, did you want to just give a bit of a perspective on the value of this project and how your team had that success?
Yep, thanks, Patrick. So I guess I'll just rewind a little bit. Queensland is a little bit behind the rest of Australia and the world. It traditionally has been, and the approach to sewer planning and network analysis has been based on the traditional peak wet weather flow approach. So typically 5 times average dry weather flow, and a static, steady state analysis of sewer networks. So the project here is the Slacks Creek sewer catchment, and the traditional approach to that had identified a very high cost augmentation being required of the trunk main, a little bit downstream of the inset shown there on the western side of a creek to the left of the screen. So that augmentation was a very high cost, and once we actually we developed a calibrated model, did a flow survey, developed a calibrated model. Once we had a calibrated model, we found that, first of all, the problem in that particular location wasn't quite as severe as we had thought. Not only that, there was other overflows in other areas that were more of a problem. But we also found that there was a significant time factor at play. So the catchment on the west side of the creek here is a little bit smaller and has a faster response time than the catchment on the eastern side of the creek. So there's parallel mains running either side of the creek. The peak and flows on the west side of the creek move quite a bit more quickly through the catchment than the peak flows on the east side of the creek. So in lieu of building a large diameter, high cost parallel duplication of on the western side of the creek, we actually just, I believe the construction of this is recently finished, put a cross connection in across the creek at a significantly reduced cost to take advantage of the spare capacity in the main on the eastern side of the creek. It's a spare capacity that's there in time. If you were to do a steady state static analysis of this network, you wouldn't have discovered that. So there were other facets to the project, but that was really the heart of it. And yeah, as you can see, it cost about $250,000 to undertake flow monitoring, model calibration, and the following on planning for the infrastructure. but a significant saving in capital works and a good outcome for council.
Fantastic. So in addition to having successful project work, it's also it's worthwhile to revisit the why behind the reason you're modeling, and that's through your objectives. So if referring to, say, the specification and sewer model build and calibration document written by the Big Four out of Melbourne, so Melbourne Water, City West Water, Yarra Valley Water, Southeast Water, I believe GHD was involved in the drafting of this particular document, you can see the wide array of objectives and how fundamental models are to these organizations in particular, as well as across Australia and the greater Asia Pacific region. So if you want to get better return on the investment you've done with your modeling work, it's best to also revisit the reasons in which you're modeling to begin with and how you can make better use of them as well. So from a technological perspective, when you talk about live sewer modeling, models are now entering the operation space where operators are going to be able to run forecasts about what's going to hit the network based on an incoming event. So there's advances in technology where more people can be using them, as well as it's just going back to the fundamentals. If you just look at the list here from this particular document, there's definitely ways in which you can make more use of your particular models. So we encourage you to revisit the objectives to maximize the use. And there's also a strong regional consideration when you're thinking of these objectives. So Matt, did you want to speak to the difference maybe between how they design in Victoria versus regionally in Southeast Queensland?
Probably the first comment I'd like to make is that Australia doesn't have combined sewer stormwater systems. We do have separate systems. That being said, we do have older networks that suffer from inflow infiltration. So when we analyse our sewer networks, wet weather flows, performance in wet weather conditions, we still do refer to storm events. So I guess in Melbourne, they do refer to a 5-year average recurrence interval or ARI event and containment of that event. Compared to Queensland, Melbourne has much lower rainfall intensities. A 1 in 5 year event in Brisbane and Queensland particularly would be 5 or 6 times the rainfall intensity. And if you were to apply this type of a standard in Queensland, probably the capital works to do that would be unaffordable. So Queensland doesn't have a standard like this at the moment, and a lot of water authorities are playing with different standards and trying to balance a reasonable containment standard or overflow frequency standard with and community expectations and expenditure. And it's a bit of a balance to do that. So I guess Logan City Council did start with a 1-year ARI containment standard, and that was applied successfully in that Slacks Creek catchment, which I spoke about earlier. But we have some other catchments where it hasn't worked out as well and has resulted in pretty significant expenditure. So we're now moving to a bit more of what we call a risk and effects-based containment standard. So really starting to look at catchment-specific issues and risk to the community and community expectations again, and risk to the environment of particular overflows. So some locations the overflows might not have as high a risk, other overflows the risk might be higher. And the industry as well is moving towards an effects-based containment standard, which really is a risk base is about a qualitative assessment of risk. An effects-based standard would be a more quantitative assessment of risk. So that's quite an intensive thing to do, not particularly appropriate for all projects. There's a lot of work involved. Receiving waterway models required. You need to have sediment transport and pollutant transport active in your models to do that. But certainly for high sensitivity catchments and high expenditure type projects, they're really useful. And I know Queensland Urban Utilities are currently working on a project in that space and getting some really good outcomes.
So for the main component of today's presentation and webinar, Matt and I are going to walk through the calibration approach. So we're going to go through the model setup from a hydraulics and hydrology standpoint, cover the adjustment having an expert practitioner here who's on the model on a regular basis and is fantastic at what he does to be able to gain insights from, how Matt adjusts land use categories and runoff services to get a better agreement in his model. And we're actually going to also cover something called the ground infiltration module, which has a bit of a reputation on something that's quite difficult to use. So hopefully we're going to be able to shed some light and make it more worthwhile in terms of when to use it, why you would want to use it, and how. And in that, we're going to cover the calibration process, just give a quick overview. And then software features within InfoWorks ICM, as well as InfoWorks ICM Suite. When you upgrade, you'll have access to a performance database called TSDB. So we'll be able to get to that as well on how to keep your models up to date. And from an investment standpoint, how to lower the rate at which your investment is depreciating because your models are actually kept up to date by automatically updating them as you please. So at this point, Matt, did you want to just jump right into it and give an overview? We have some maps here we can show, and then after 4 or 5 slides, we will jump into the software and be able to demonstrate how the calibration was accomplished.
So we'll work through this by way of a case study. So what you're looking at is the Beanley wastewater catchment, and we've calibrated, Logan City Council and the Logan Water Infrastructure Alliance calibrated this model early last year. So the figure on the left just shows the catchment. There are three main catchments draining to pump stations, which pump to a wastewater treatment plant on the top right-hand corner of the screen. On the right-hand side, you can see a schematic of all the pump stations. So there's 45 pump stations in this catchment, 330 kilometres of pipelines, and 50,000 EP or equivalent persons. It's not a huge catchment. Council does have bigger catchment than this, but it is quite complex due to the number of pump stations, and there's quite a few pump stations that inject into common rising mains. So there's a few challenges with setting the model up there. Okay, so we did 2 flow surveys in 2016. Bit of a lesson learned here. It just worked out that we had to do 2 flow surveys, but ideally you will do 1 that covers the whole catchment. The first flow survey on the left there was done primarily chasing inflow and infiltration, source detection work, but the flow monitors used there are also useful for model calibration. On the right-hand side, the flow survey primary purpose was for model calibration. So, it ended up covering a 6-month period, and there wasn't overlap between the flow surveys. So it does create a few challenges in the modelling space. So the main thing there is if you can get all your flow models in the ground and conduct a flow survey over a common period, that is certainly ideal. One of the challenges with Australia is that we have a highly variable climate. So in this particular year, it didn't rain a lot at the first half of the year. And our wet season typically spans from about December through to March or April. So go to the next slide, Patrick. Oh. Sorry, this is the network. So yeah, this is the flow survey. So this is the second flow survey. So this was started in April. And as you can see from the graph at the top there, we didn't get a lot of rainfall all the way through to June, which is highly unusual for Queensland. Typically, we expect probably 80% of our annual rainfall to have been completed by April, May, and then it can often be very dry for the remainder of the year. Now, the flow survey period was scheduled to be, I think, completed by probably May. Luckily, we've got a very understanding client who was happy to keep the flow monitors in the ground and spend the extra money to get the data, and we're very lucky to actually get a couple of significant events. So you can see the first significant event occurred around the 2nd of June, and it was call it 2 EY, or an event that should occur at least twice per year. And it was probably characterised by lower intensity rainfall over a couple of days. And then within a couple of weeks after that, we had another very small event, and then a week or so after that, we had quite a significant event, which was a 0.5 EY or a 2-year ARI event. And that really is a great sewer response and great rainfall events to use for model calibration. So that was a period we focused on for calibrating the majority of the model. I should have mentioned, so for the remainder of this, we'll just be focusing on one of the catchments I alluded to earlier. So you see on that screen there. The other catchments were calibrated to the first flow monitoring period. This one probably had more interesting rainfall response in the sewer, so there's some good things to talk about.
So Matt, at this point, did you want to go into the model?
Yes, let's do that. Okay, so we'll just open up the catchment first. Okay, so when you open up, just a little bit of basics here, but when you first open up a model, you often you see the subcatchments and the drainage arrows. It's great to have a theme ready to go, and Patrick just dropped a theme onto the screen. I find it a little hard to look at all the drainage arrows and only really turn that on when I zoomed in a bit more. So I think it's great to have the gravity mains and the pressure or rising mains separate. So you can see there the pink theme is for the sewer rising mains, pressure mains, and the green are the gravity mains. You can even differentiate your trunk mains from your articulation mains as well. The theme in InfoWorks is pretty powerful, and you can really do anything you like. I also normally have a theme for my runs that will show which mains are surcharged and whether they're surcharged by backwater or capacity, and also where your overflows are. And you can even have a theme that will tell you the volume of overflow by the number of concentric circles. So it's pretty powerful. So let's dive into, I guess, first of all, a couple of tips on the initial model setup. So when we're talking about calibration, you've got your hydraulic model, which is the sort of the below ground assets, the physical model, and then your above ground part of the model, which is really your hydrology. Most water authorities would already have a model set up, and the accuracy of the asset data behind that model, my experience is to go by, it can be patchy. We have some of our models built on drawings that date back to the 70s. Some of it's very recent as constructed data. And even the very recent data can have some issues with it. So when you're first setting up your flow monitoring survey, I'd always recommend some spot manhole surveys, at least a couple of manholes upstream and downstream of your flow monitor gauges, and some CCTV investigations as well is also really useful. LiDAR data now is available, which is a powerful tool and pretty accurate, a good way to get, or at least check, manhole cover levels. So there's probably quite a bit you can do before you start calibrating in terms of the physical network assets. It's never going to be perfect. But it's worthwhile investing a bit of time and effort at the front end. It's also good to be able to, and if you're getting consultants to do this work, it's good to get some, give the consultants access to as constructed drawings, probably when they need them. Often as you're going through the calibration process, you find something that the observed and predicted data not quite aligning, and it may be an issue with your asset data. So I regularly refer to my as constructed drawings, and sometimes if I really have to, I'll even send a survey crew into the field to confirm some levels or a pipe diameter or something similar.
Matt, do you have a data hierarchy that you follow where, say, your ASCON drawings are more valuable than an as-built drawing from the 70s, or say a survey that was completed is more trustworthy than the ASCON drawing?
Absolutely, and we use make heavy use of the data flag system in InfoWorks to track that. So we know exactly how the data in the model has been entered and what the data source of that is.
Okay.
And I actually have to thank Ian McDonald at the Logan Water Alliance. He's got a really rigorous system, and his flagging system is excellent.
Excellent. So we're into the flow survey data now, and you can see there's been simulations that have been run. So the rainfall is plotted against the depth flow and velocity. So the way it's kind of posted in the software is you have your flow monitor location, as well as your asset ID in which the flow monitor was attributed to. Matt, was there one in particular you wanted to go through?
Yes. So I thought we were going to go through a little bit of the model setup first, or do you want to jump straight into this?
We could go into the model setup. So
okay, so just a little bit on I think talked a little bit about the hydraulics. I'm going to assume people know that pretty well, but I think it's the hydrology component of the model that can be a little bit of a mystery. So I just want to go through a little bit of the setup of that aspect of this model. So I've just opened up in a grid view the subcatchments. So there's obviously a huge number of catchments in there, and a lot of this comes from, there's a lot of information from our property layers. We have sort of land uses in there, catchment sizes. Usually our catchments are just the properties themselves. We don't typically include roads and those sort of things. So just areas that could potentially contribute inflow and infiltration to the sewer. And there's obviously the direct property connections themselves. But in terms of the hydrology aspects, the key things to start with here are the land use IDs and the ground infiltration IDs. So I'll just first of all talk a bit more about the land use IDs. So they are set up based on our flow monitor location. So each flow monitor has a catchment, and we assign each sub-catchment a land use ID based on the flow monitor catchment that it's within. So let's go to the land use tab. So you can see on the land use ID tab there, the flow monitor IDs. And the key thing, so we have one of those for each flow monitor and also for each pump station. So we use, as well as the flow monitoring data, we also use pump station SCADA data. In some cases, the pump stations have mag flow meters on them, so we get flow data directly. In other cases, we only have pump start and stop time, so we convert that into flow data using assumed pump capacities or actual pump capacity data if we have it. So the key things here is for each land use ID, we set up 3 areas, and that's their runoff surfaces, and I'll talk about those in a second. But we have 3 runoff surfaces, typically something representing road, roof, and pervious areas. So the key calibration parameters here are in the default areas. So that is effectively the area within those flow monitor catchments that contribute back to the sewer. So I mentioned before, Australia has separate systems. So typically we see very small percentages that actually directly contribute back into the sewer system. For a combined sewer system, the percentage might be 80 or 90% or more. But typically for a separate system, we'd expect to see something in the order of an older system, you might get 3 to 5%, or a really poorly performing system, 10%. For a newer system, the number could be down as low as 0.1%. So I'll just jump to the runoff surface tab. Sorry, I should have just mentioned. So those default areas, they're probably 3 of the fundamental calibration parameters that you're tweaking as you're going through your calibration process. So the runoff surfaces give a little bit more information about the rainfall routing aspect of the land uses. So as I mentioned before, and you can do this any way you like, of course, but the approach we've adopted is to have 3 surfaces for each flow monitor catchment, something representing road, roof, and pervious areas. For the impervious areas, we use the fixed runoff approach, and for the pervious areas, we use the new UK or PR method, which is extremely useful because it actually tracks varying wetness conditions, and it's really good for looking at long-term performance as different storms move through the catchment. So key calibration parameters here are your routing values and your fixed runoff coefficients. So routing values is basically the time taken for flow to move across that surface and into the sewer system. For your impervious surfaces, they should be typically small, indicating a fast response. For your pervious surfaces, you'd expect something a bit larger. And again, they are key calibration parameters. A really important thing with all these parameters is to understand what their reasonable range is. So if you use a number that's very large, particularly for the runoff routing value, anything larger than 50, you will get some unexpected responses. I've seen very high numbers up to 600 for a routing value. And if you do a long period simulation with that, you'll find rainfall still moving across that surface after 2 months after the rainfall events occurred. So there's some tips and tricks to watch out for there.
Do you have a reference of initial starting parameters that you use?
I don't, but the Melbourne Water document you alluded to actually has an excellent set of a range of parameters for each parameter you consider here, and I've actually referred to that fairly heavily. There's a fair bit of trial and error as well, and just understanding what the ranges are. And there's some guidance also given in the help within the ICM model.
Yeah.
Okay, so that's the runoff surfaces. Probably the next one. So,
We'll go to the time series, and then or did you want to go to ground infiltration module in the PowerPoint?
Yeah. So yeah, we'll jump to the groundwater infiltration module now.
Yeah.
Patrick's just loading up a slide that's going to show a little bit of the theory behind sewer responses and where groundwater infiltration fits into that.
Yeah, so we're not covering too much theory because we want to make the most of having Matt here. But in terms of the ground infiltration module, the most common use is to provide a large, highly attenuated response to rainfall. So such a response is often observed in the flow survey data as Matt was showing earlier. So it originates from groundwater or rural or underdeveloped parts of the catchment. With runoff in particular, there is some rainfall which enters the sewer and some which does not. So the key to utilizing the GIM, as we call it in Forks ICM, is that it allows a proportion of the rainfall which does not get into the sewer as runoff initially to get there by other means.
Yeah, so the GIM or groundwater filtration module within InfoWorks has two storages. So in the graph on the left-hand side, there's the soil store, which is that yellow band, and the groundwater store, which is the light blue band. So I guess traditionally people think of the groundwater component of wet weather inflow and filtration as purely the slow response. But as you can see, looking at the yellow slither there, it does contribute to the fast response and peak of the event and volume. So if you're getting inflow, infiltration, or infiltration into your sewer from the soil store, it can happen quite quickly. And the InfoWorks GIM is a really useful tool to estimating what that is. Okay, so let's just open up the GIM module. So here we are. So
we're still in the subcatchment data associated with that particular network you were showing earlier. So essentially you've just switched tabs within the catchment grid view.
That's right. Yep. So the same approach as for the land use IDs, we set up a groundwater infiltration ID based on the flow monitor catchments and our pump stations. So the key, so typically we talk, there's two stores, or two buckets. There's the soil store and the groundwater store. Most of the infiltration does tend to happen through the soil store unless your sewers are very deep and inundated by groundwater. Generally, unless you have groundwater monitoring data, we do try and get the response purely through the soil store. If you do have deep, large sewers and you're confident there is a groundwater response and you have access to some groundwater monitoring data, it's certainly worthwhile calibrating the groundwater store, but it does add a lot of complexity to the calibration. So you can turn the groundwater store off by setting the base flow threshold level, which is there, lower than the infiltration threshold level, which is over here. So that's the case for this particular model. So the key calibration parameters here are the percolation coefficient, which is basically how fast the soil store, in this case, discharges into the sewer. Smaller numbers being faster, larger numbers being smaller. The percolation threshold, which is a pretty important one that I've only come to grips with relatively recently. So basically the higher the threshold, it's effectively like a bucket. So the higher that threshold, the more the bucket has to fill before the network starts. discharging back into until the groundwater starts discharging back into the sewer. The other one is soil porosity. It's probably not really a calibration parameter. You should be calculating that depending on some geotechnical information if you can, or otherwise assume something reasonable and probably leave it fixed. Really, the percolation threshold and the percolation coefficient are the primary calibration parameters that I use. Okay, so now I'll just talk a bit about some lessons learned and some results from this the calibration of the Bramley catchment. So I guess I'm going to show you this. I've got 3 runs on this graph. We'll just go to BL14 first, Patrick. It just does show a bit of the evolution of my thinking and the calibration of this particular model. So the green line is the observed data or the flow monitor data.
Right now, we're just progressing through the different gauges of flow monitor data that are loaded into the software already.
Yep. Okay.
So, yep.
So I'm just going to zoom into a couple of our storm events. So this particular model has only been run from the start of this first event here, which I'll refer to as event 6, there's a number of them, and the second event, which I'll refer to as event 8. Because there was a long period of no rainfall preceding those events, it was fairly safe to run it from that period. If there had been more wet weather preceding that, I would have liked to have increased the simulation time. And probably something else I should mention, if you can, you should be running full flow monitoring period simulations during calibration. If you're not doing that, you're going to be missing antecedent conditions and the impact of storms, even small events that have occurred on catchment wetness and the like. If computational requirements are too much, you can break it down to single event simulations if you start using hot start files, and InfoWorks does let you do that. But even then, obviously the hot start file you've run doesn't take account of the changes you might have made as part of the calibration process. So you really should be running a full period simulation pretty regularly. So I'll just zoom into the first event. So yeah, as I mentioned, green line is the observed data, and there's 3 other lines. There's a fawn, light brown, dark brown, and a blue line. So the legend on the left-hand side explains what they are. So the progression here was first, I was actually running single event period simulations and then doing probably once a week or once every 3 days full period simulation. So I would first start trying to calibrate to the first event, event 6, and then I would try and calibrate to event 8. And I had, at this point in time, I hadn't done anything with the percolation threshold, which we talked about in the gym, and I just had it set at, I think it was 0. So basically that means that as soon as rainfall enters the soil store, it starts discharging immediately into the sewer. So I just found it very difficult to get a good fit with when I ran the full period simulation for these 2 different events. So you can see for the event 6 calibration, I matched event 6 very well, but then for the event 8 calibration, you'll see that the calibration was good for the second event. It was massively over predicting flow and level for the first event. So I'll just zoom out and show you that. So this is the calibration for event 8. So here you can see event 6, that's depth at the top there, barely even responding to that event, whereas for my event 8 calibration, the response was much closer to the observed flow. And as I said, that was because I had the percolation threshold set at effectively 0. So once I started tweaking that parameter, what I was able to do was, because it had been dry beforehand, the soil store has to fill up a little bit before it starts contributing to the sewer. So we found that focusing on event 6, the gym didn't really contribute much at all to inflow to the sewer during that event, because it was probably a longer duration, lower intensity event. So I set the percolation threshold accordingly, and it did fill up the bucket, but the bucket only started contributing a bit of slow infiltration towards the end of the event. Of course, that bucket does stay relatively full. You do lose flow to the groundwater store and through evapotranspiration over time. But then this small event here did recharge it slightly. And so by the time we got to this event, that soil store was still close to full, and there was almost an immediate response of the soil store back into the sewer for the second event. So yeah, once I had that percolation threshold set properly, I was then able to get a good calibration, and that's the blue line there. I'll show another gauge quickly. So there's a similar thing happened there. So you can see for this gauge, and this is an interesting one because you can see the pump response from an upstream pump station. But so a good fit for the brown line. So that was the initial calibration for event 6, but a big over response for the event 8 calibration. Massively overestimating level there, and then similarly for our event 8, the model I calibrated to event 6 was hugely under-predicting sewer response, whereas the event 8 calibration was predicting it more accurately. So yeah, once I set the percolation threshold appropriately, we did get a much better response for both events. Okay, we'll go back to the presentation now. Just wanted to mention a few things about one of the other functions within the model, which is the scatter plots. So InfoWorks allows you to plot velocity versus depth plots from the flow survey, which I had up before. So you can plot the observed against the predicted. And scatter plots are a really useful tool, and they can tell you a lot about sewer performance that you might not be able to ascertain from the just looking at the flow data itself. ADS are a company that do flow monitoring, and the company that we actually prefer to use most of the time. They have an excellent poster, which you get download from their website, I believe, which describes the different types of scatter plots and what they mean. I'm just going to go through a couple of things here that are pretty useful. So the first scatter plot on the left there is basically showing typical in-pipe performance. So there's a slightly exponential relationship between depth and flow. There's nothing particularly unusual happening there. That could be described with probably the Manning's formula. The graph on the right is a bit more interesting. So we're seeing the relatively, slightly exponential, relatively linear increase of depth and velocity up until we get to depth of probably about 150 millimeters. Yes, 100 millimeters. So this is actually in a pipeline that's 375 millimeters in diameter. So you would expect the linear increase in depth and flow to be all the way to the top of that pipeline. So in this case, it's not. So we're actually seeing, when we get to 100 millimeters, we see the depth and velocity relationship to actually go backwards. So we're seeing increasing depth with reducing velocity, and that's because there's backwater conditions that's been established in that pipe. So we're actually in that particular part of the network, the capacity of the pipe is much lower than you would expect, and this is not something you'd ever be able to get from a static model analysis. It's something you definitely need a calibrated model to understand properly. So you see a bit of that's the backwater performance up until we hit about 200 millimeters, and at that point, so this is actually a 200 millimeter pipe. At that point, we hit surcharge conditions. So you get basically, as depth increases, there's no further increases in velocity and therefore capacity. So in this case, we had surcharge conditions right up to 800 millimeters, but no overflow in this case, just surcharge.
Are these particular types of graphs, are they used for movement of sediment and debris?
You can also ascertain that kind of performance from these graphs as well. So again, the ADS poster on their website does explain all these in quite a lot of detail. And often you'll see different types of performances from the theory mixed together in the same sewer, but you can certainly see the movement of sediment, debris. You can even pick up large objects or blockages, that sort of thing. They're quite a powerful tool. On the left, you see similar to the second graph I showed before, with linear increase between relationship between depth and velocity, backwater conditions, and then surcharge. You're also seeing an overflow up here. So once you get that performance relationship, that's what we call a flat top. So depth not increasing, but velocity increasing. We're starting to see an overflow of some description. You're also seeing something here called hydraulic hysteresis. So basically, as flow increases at the front end of an event, you're less likely to have surcharge or backwater conditions in the downstream sewer. So your rate of velocity and depth increase would be a bit greater as the surcharge goes upwards. But then once the event's started to pass, you are more likely to have backwater conditions in the downstream network. So typically you'll see a different relationship on the receding event. So that's a bit of an interesting phenomena. And then on the right here, we're just seeing something again a little bit similar, but the surcharge is a bit different. We've got a bit more of a relationship there. So there could be some sort of another overflow downstream or a high level pipe influencing behaviour there.
So shifting from projects and from a practitioner's point of view, let's focus now more from a technology side of things, the software end of it, in terms of what are the everyday aspects of InfoWorks ICM that really contribute to effective project work, to saving time on your calibration, to running multiple simulations, to working in teams of 4 to 10 people in terms of contributing to the same model at the same time and having the ability to understand what changes were made and to track those changes over time, to revisit previous versions of your model. A lot of these are built-in capabilities into the application. So just wanted to take this opportunity to ask Matt what really stands out to him in terms of everyday project use and how he can be really effective in the application.
Using calibrated models?
Yeah. So do you find yourself using the multi-user editing aspect, and do you ever have to go back in time to look at the commit history?
Yes. The multi-user edit is very powerful. In fact, we're working on a master planning project at the moment where we have 4 users working in the same space on the same model, and it's mostly successful. If something does go wrong, you do have the commit history there, and it's quite useful to go back to that. In fact, in preparing for this presentation, I used that commit history to go back and pull out some of the earlier calibration runs, which I showed you, which weren't the final runs. So it's a very powerful tool. And
then when you have, so on the consulting end of things, or on the utility or council end of things, you have multiple sources contributing to the model itself. Do you find yourself using the data flagging so you can understand where, was it GIS or was it a design drawing, the source of information?
Yep, the data flagging is probably critical to use. I would hope that anyone with a hydraulic model has made heavy use of it. Particularly when you're going through calibration, understanding the hierarchy of data is really important. What you can, maybe something's derived from a GIS or an older ASCON drawing with a questionable benchmark for survey. Go and change some of that asset data to suit the calibration. But where it's from a recent ASCON or a recent survey, you'd be less inclined to want to change something like that.
Yeah, and then ICM also has a data validation function that essentially lets you, it corrects and lets you know where there's errors in your data. Say if you brought it in from GIS and you're missing an invert elevation, it'll flag that to you and won't allow you to run the model until you have the adequate data before you hit simulate. What size of networks are you dealing with at the Water Alliance?
We have pretty large networks. I think our biggest one, it might have 30 or 40,000 nodes.
Yep.
So it's very large. And it pays to have a stable model. So a tip I've got is when you're doing your initial runs, you turn on the run diagnostics in the model and look at the time step halvings. You can also see where you're getting a lot of time step halvings in the run dialog boxes. So really have a look at that and focus on where those are occurring and try and resolve those. To anything you can do at that stage to increase your run time is going to save a huge amount of time as you go through the calibration process.
Yeah. And then you also have the progression of technology from a time series analysis point of view and connecting your models and helping them go live. So that'll actually tie into the next portion where the workgroup and enterprise configuration aspect of InfoWorks ICM is incredibly valuable. So to have the ability to kick off a simulation on a central server that has multiple cores available for your simulations is incredibly valuable. we often get though from clients, and they lament and they say, we're not a large utility. This application is too advanced for us. And the thing I can say to that is ICM can be set up on a single laptop, and it can be a high spec laptop, and you can go about your modeling work, or it could be advanced and you could be like some of the larger utilities in the greater Melbourne area, where they have 7 or 8 user interface model build licenses and 1 or 2 simulation engines, and they're utilizing a high specification server. So Matt, earlier this morning you were letting me know about kind of your setup, and it sounded quite impressive from it was just a desktop, right?
Yeah. So I'm lucky enough to have a supportive IT group. So I guess I started off doing calibration with a standard desktop PC, but we've moved to getting something pretty beefy. So we have, at the moment, I've got a dual 2.3 gigahertz Xeon processor in my machine. It's got, I think, a total of 14 cores and 28 threads. So that's really optimal for running a large model over a long simulation period. In fact, it's so worth investing. That this machine, I think it costs about $20,000 Australian, which sounds like a lot, but when you're talking about a calibration project which might be worth 100,000 or more, resulting in capital works that are going to cost millions, it's really worth investing in. It also just increases your efficiency enormously to have a powerful computer. Doing any kind of a calibration exercise on a laptop, as I'm sure people out there are probably aware, can be really challenging. You're really quite limited to the number of parallel cores and processors you have on any laptop, even a really high spec one. So if you can possibly convince your IT department to invest in a decent hardware, it goes a long way to helping with model calibration particularly.
So speaking of getting into more modern day setups with your models and having more people gain access to the models themselves, I just wanted to take this opportunity to discuss the time series database technology in InfoWorks ICM, as well as it's the technology that underpins ICM. So it's a performance database. It allows you to connect directly to your telemetry and SCADA data. And once it's connected for good in terms of it'll automatically update. So you're no longer manipulating outside spreadsheets. You're now forming direct connections. It's scalar, so the data is either 1D or spatial in terms of 2D. And you can bring in forecasted or observed data from the field. It's also, from a performance standpoint, historically powerful in the sense that, to use an example, Thames Water connected to live data sources back around the London Olympics back in 2012. And they are still utilizing that same technology to bring in all their live time series data for their live operational models as well. So it's an incredibly powerful database, and it allows for sharing and user editing. So what you can see on your screen here is some advanced theming from a direct connection to a meteorological website where it's pulling in forecast spatial rainfall. So you're able to access this technology in InfoWorks ICM suite, or it's also the technology that underpins ICMLive. So Thames Water in the UK, Southern Water, Meta Water in Fukui, Japan, they're all running live operational models that are utilizing forecasted spatial rainfall. I'm just going to show what that looks like in the model. So I've got a workspace that's pre-prepared to show the rainfall visualization. So just in the geoplane, I have a simulation that's already been completed. And now I'm kicking off the simulation. So for users in Australia, you're able to connect this database technology directly to the BOM, the Bureau of Meteorology website. Apologies for just using acronyms. So you can see I've got some dynamic themes. It's letting me know what's happening in my network. at this particular time. But the key here is if this is a forecast scenario or even a present scenario that's happening in real time, you can now model spatially the varying intensities and where things are going to hit your network. And just to show how to add this, so just say tomorrow you have InfoWorks ICM suite and you want to connect to the Bureau of Meteorology website. I just create a new item in my model, and it allows me to directly map this data source to the BOM, as well as there's alternative sources that I'm able to map to. And just to show what the time series database looks like on the back end, it's a grid view, and I'm able to show the flow level, surcharge level, the velocity. These are direct connections, whether it's telemetry or to disparate data sets that I have on my C drive buried away on an old laptop. I'm able to connect to that Excel file or spreadsheet file and bring it in. So it's a single source of bringing in disparate data sets as well. So it's that single point of truth. And when you're using ICMLive itself, it'll also automatically update the live data feeds as well. So you can see when my latest update was, what the latest data was for. And you're also able to do pre-processing. So within the time-varying data connector aspect of InfoWorks ICM, I can do pre-processing. So if I'm measuring intensity in the field and I want to convert it to a cumulative volume over a period of time, or if at a sluice gate I have a radial angle that I've measured, I can also write a script to convert that into a particular flow. So anything that I have existing in a spreadsheet, I can go and utilize as pre-processing. If you also think of the way rain data works, often it falls out. You'll have a rain gauge drop out. So here you're able to set up multiple inputs, where if I have multiple rain gauges and one drops out for a particular period of time, the TSDB technology will understand that the data feed has dropped out and it'll pick up an alternative rain gauge kind of thing. And then again, the time series database technology is a way of connecting to ICMLive. So ICMLive is a way of putting the technology in the space of operators for operational decision support. It's also a way of keeping models more up to date. So if I'm bringing in my rain gauge information, my water levels, my flow meters, my pump operation, and I'm using my planning model as a technology that underpins that, now all of a sudden you have the opportunity in your organization to create operational forecasts. So the key components of ICMLive are simply it links to telemetry and other data sources to receive real-time information. It runs regular automatic simulations. So it's automatically updating the time series database and then kicking off and running the simulation. Its run intervals can be reduced automatically if, say, it hasn't rained in 2 or 3 days, or if a rainfall event is anticipated, it'll start automatically kicking off the simulations if you set it up that way. It forecasts levels, flows, and water quality across the whole catchment, and also if a particular threshold has been exceeded in the network, you can set it up to kick off alerts.
Patrick, can you tell me if any water authorities actually have allowed this to take any automated control over their systems? So, for instance, where you're seeing a storm approaching from a particular catchment, you might hold up a pump station in a different catchment in favour of pumping more from a particular pump station to minimise overflows.
Yeah, I believe that's a nice example from Thames Water. There was a scenario where they had an incoming event and they had the option of pumping flow, and if they didn't pump, it was going to overflow, into a receiving waterway. So they were able to use the technology to run a scenario in which they understand and alleviate that from happening. So as you can see, this is the operator client for InfoWorks ICM. So ICMLive, I should say.
Yeah, I haven't really used the time series database functionality much, but I can see some amazing opportunities for it. Even things as simple as you want to do some maintenance work for a part of the network, and you can tell your operators how much flow they can expect in the network at that point in time, and therefore what kind of bypass pump size they need. CCTV surveys, you can only have a certain depth of flow in a sewer to actually do those. So if we can understand what the depth of flow actually is at any given point in time, we can get the crews out there at the right time of day and then look at bypass pumping if required to do that. There's a lot of guesswork in that area at the moment. So
yeah, and the particular model has been used to detect blockages, avoid spills. It acts as a technology for safety for construction crews if they're operating on the network, to warn them of an incoming event or to establish a bypass alternative. It's utilized to prime pumps and RTCs for incoming events. It gives a sense of live availability of storage in your network. Operators often come over to the planning engineers and they ask, how much time do we have until failure based on storage availability? So you get more engagement with the models. They become more valuable to your organization. So
you can even use that information to help with setting alarms and critical alarms in your network. So if you've got a few hours worth of storage for you, get an overflow following a pump failure, you can use that to inform when your critical alarm should kick in, which can be good for preventing operators having to get up in the middle of the night to address an outage somewhere that maybe they don't need to.
Yeah. So that kind of reverts back to our original kind of theme for the presentation in terms of increasing the ROI on your modeling investment through better model calibration, better project work, revisiting the objectives, the why, the reason you're modeling in the first place, and then making better use of the software, the technology, such as time series database to, if your models are up to date, the value of them won't depreciate as greatly and drastically, and you can make better use of them by them being more up to date. And then furthermore, if you're pulling more people in through technology like ICMLive for operators or your planning engineers to have up to date models, that only bodes well for the investment you've made. Just some quick special thanks for how this presentation was put together. Special thanks to Sandy Viren and the Logan Water Alliance. They graciously provided the model for educational purposes on this presentation, and we're extremely grateful for them providing the model. That was incredibly valuable. The Logan Water Alliance modeling team and the incredible project success Matt and your team has had. And then just a personal special thanks to Nathan Gertz of our product management team, who helped set up the spatial rainfall and the time series database demonstration. And I just want to give special thanks to my man Orlando and the technical support team. Orlando, I can only imagine the amount of inquiries that are coming your way after this presentation. So thanks so much for your help with those questions that are inbound to you.
So I think we've had some questions come in from the webinar. So do you want to?
Yeah, we'll just cover a quick questions. We're a few minutes past the hour, so we'll just keep this tight. The first question that came in, and it was relating to licensing in terms of gaining access to the time series database. So it looks like this person is an existing InfoWorks ICM user. And they're asking, do I need ICMLive to access the time series database? And the answer is no. You just have to upgrade to InfoWorks ICM Suite. So it's just coming up one license level to access the time series database technology. And then if and when you wish to progress to ICMLive, ICMLive shares the same interface with InfoWorks ICM. The only difference is it has TSDB that comes with it, and it deploys up to an operator interface that is a read-only interface that allows you to run scenarios based on your forecasted situation in the network.
I had a question as well about just the value of flow monitoring. So I guess a flow monitoring survey program can be expensive. At council, I know we spent quite a bit of money on that, and often it comes out of operational budgets for water utilities. And there can be question marks over the real value of that. So I guess without that data, you can't build a calibrated model. And without a calibrated model, you can't really truly understand the performance of your sewer. And you can be spending money either in the wrong place or too much. So it really helps optimize and inform your capital works programs and improve the performance of your sewers. So without that underlying data, you don't get those outcomes. And those outcomes are, you're talking about millions of dollars. So the relatively small investment in flow survey is really worth it in the long term.
I've got two quick questions here about the groundwater infiltration module. The first question is it available in InfoWorks ICM? And the short answer is yes. Just go to the help file, read up on the theory behind the GIM. The help file is incredibly extensive, especially in the theory around the GIM. And it's available in your InfoWorks ICM SE license. And then you'll find it in a tab within the subcatchment grid view in InfoWorks ICM. And the second question is for Matt. Do you always use the GIM in all of your calibrations?
Yes, we do. Yep, absolutely.
So from the start of when you've measured data, you don't even start your calibration without actually considering those parameters?
We'll probably set some default parameters first, and there's a hierarchy of how we move through the calibration process, and we do start with those high-level contributing catchment areas, and the GIM is probably the last thing that you're tweaking, but it's certainly in there from the start.
Okay, great. Okay, so just in the interest of time, we have unanswered questions that we're not going to be able to get to. Apologies for that. If you want to email me, education@innovyze.com with any follow-up questions to the webinar, please do so. And I just wanted to take this opportunity to thank all the people for tuning in. We really are grateful for your time. We're excited about the project work that was completed in InfoWorks ICM. Thank you, Matt. And the technology and what's possible now with our models, they're more fundamental to our organizations, and that's incredibly exciting for Innovyze. So yeah, just special thanks, and hope everybody has an amazing afternoon or the rest of your day, and we'll catch you next time in the next webinar in the series.
Thank you.